Hello guys and welcome to my channel. In this session, I want to talk about verification process. Well, if you want to find out more about this process, then don't miss this training session. And as always, have a good one. The purpose of the verification process is to provide objective evidence that a system or system element fulfills its specified requirements and characteristics. As described here, this process is an instance of a verification process applied to a SOI or any system or system element that compose it to establish that it has been built right. The verification process can be applied to any engineering element that has contributed to the definition and realization of the system itself. For example, verification of a system requirement, a function, an input or output flow, a system element, an interface, a design property, a verification procedure. The purpose of the verification process is to provide evidence that no error or defect or fault has been introduced at the time of any transformation of inputs into outputs. It is used to confirm that this transformation has been made right according to the requirements and selected methods, techniques, standards, or rules. As is often stated, verification is intended to ensure that the product is built right, while validation is intended to ensure that the right product is built. Verification is a transverse activity to every lifecycle stage of the system. In particular, during the development of the system, verification applies onto any activity and product resulting from that activity. This slide is the IPO diagram for the verification process. The verification process includes the following activities. Prepare for verification. Develop a strategy that prioritizes the verification actions to minimize costs and risks while maximizing operational coverage of system behaviors. Establish a list of the items for verification, including requirements, architectural characteristics, or design properties, and define the corresponding verification actions. The approach to verification should be identified and documented at the time that a requirement is first documented to ensure that the requirement as written is indeed verifiable. This may require restating a requirement or decomposing it into several verifiable statements. For example, how do you satisfy the legitimate requirement of a system being user friendly? Establish a list of verification constraints that need to be considered. The constraints could impact the implementation of the verification actions and include contractual constraints, limitations due to regulatory requirements, cost, schedule, feasibility to exercise a function, such as in some ordinance, safety considerations, physical configurations, and accessibility or etc. Considering the constraints, plan for the methods or techniques that will be applied for each verification action. The methods or techniques generally include inspection, analysis, demonstration, or test. Note that analysis often is considered to include modeling, simulation, and analogy when identifying the verification methods or techniques, and success criteria are also defined that indicate successful verification. Establish the scope of the verification. Verification consumes resources, for example, time, labor, facilities, and funds. The selection of what must be verified should be made according to the type of system, the objectives of the project, and the acceptable risks regarding the withdrawal of a verification action. Develop the verification procedures that support the verification actions. schedule the execution of verification actions in the project steps, and define the configuration of submitted items to verification actions. Identify verification constraints on a system or system elements arising from the verification strategy that relate to specific system requirements, architecture elements, or design elements. Typical constraints include performance characteristics, accessibility, and interface characteristics. Provide the constraint information for consideration in the system requirements definition, architecture definition, and design definition processes. Ensure that the necessary enabling systems, products, or services required for the verification actions are available when needed. The planning includes the identification of requirements and interfaces for the enablers. The acquisition of the enablers can be done through various ways such as rental, procurement, development, reuse, and subcontracting. An enabler may be a complete enabling system developed as a separate project from the project of the system of interest. Perform verification. Implement the verification plan developed in the preceding subsection. That plan includes detailed descriptions for the selected verification actions, item to be verified, expected results and success criteria, selected verification method or technique, the data needed, the corresponding enabling systems, products, or services. Using the verification procedures, execute the verification actions and record the results. Analyze the verification results against any established expectations and success criteria to determine whether the element being verified indicates conformance. Manage results of verification. Identify and record verification results and enter data in the requirements verification and traceability matrix. Maintain the records per organizational policy. Record anomalies observed during the verification process and analyze and resolve the anomalies, corrective actions, or improvements using the quality assurance process. Establish and maintain bi-directional traceability of the verified system elements with the system architecture, design, and system and interface requirements that are needed for verification. Provide baseline information for configuration management. Update the verification strategy and schedule according to the progress of the project. In particular, planned verification actions can be redefined or rescheduled as necessary. Coordinate verification activities with the project manager, for example, for scheduling, acquisition of enablers, hiring of qualified personnel and resources, the architects or designers, for example, for errors, defects, nonconformance reports, and the configuration manager, for example, for versions of submitted items, requirements, architecture and design baselines, enablers, verification procedures. Beware the temptation to reduce the number of verification actions due to budget or schedule overruns. Remember that discrepancies and errors are more costly to correct later in the system lifecycle. In the progress of the project, it is important to know at any time what has not been verified in order to estimate the risks about possibly dropping out some verification actions. Each system requirement should be quantitative, measurable, unambiguous, understandable, and testable. It is generally much easier and more cost effective to ensure that requirements meet these criteria while they are being written. Requirements adjustments made after implementation and or integration are generally much more costly and may have wide-reaching redesign implications. Avoid conducting verification only late in the schedule when there is less time to handle discrepancies. Testing the actual system is expensive and is not the only verification technique. Other techniques, such as simulation, analysis, review, etc., can be used on other engineering elements representing the system of interest, such as models, mockups, or partial prototypes. A verification action describes what must be verified, for example, a requirement, a characteristics, or a property as reference, on which item, for example, requirement, function, interface, system element, system, the expected result deduced from the reference, the verification technique to apply, for example, inspection, analysis, demonstration, test, and on which level of decomposition of the system. For example, system of interest, intermediate level system elements, leaf level system elements. The definition of a verification action applied to an engineering item, for example, stakeholder requirement, system requirement, function, interface, system element, procedure, and document, includes the identification of the item on which the verification action will be performed, the reference used to define the expected result, and the appropriate verification technique. The performance of a verification action onto the submitted item provides an obtained result which is compared with the expected result. The comparison enables the correctness of the item to be determined. Examples of verification actions are verification of a stakeholder requirement or a system requirement to check the application of syntactic and grammatical rules and characteristics defined in the stakeholder needs and requirements definition process and the system requirements definition process, such as necessity, implementation free, unambiguous, consistent, complete, singular, feasible, traceable, and verifiable. Verification of the architecture of a system to check the correct application of the appropriate patterns and heuristics used and the correct usage of modeling techniques or methods. Verification of the design of a system element to check the correct usage of patterns, trade rules, or state of the art related to the concerned technology, for example, software, mechanics, electronics, chemistry. Verification of a system, product, service, or enterprise or system element to check its realized characteristics or properties, for example, as measured against its specified requirements, expected architectural characteristics, and design properties as described in the requirements, architecture, and design documents. Considerations in selecting a verification approach include practical limitations of accuracy, uncertainty, repeatability that are imposed by the verification enablers, the associated measurement methods, and the availability, accessibility, and interconnection with the enablers. Basic verification techniques are as follows. Inspection. This technique is based on visual or dimensional examination of an element. The verification relies on the human senses or uses simple methods of measurement and handling. Inspection is generally non destructive and typically includes the use of sight, hearing, smell, touch, and taste, simple physical manipulation, mechanical and electrical gauging, and measurement. No stimuli or tests are necessary. The technique is used to check properties best determined by observation, for example, paint color, weight, documentation, listing of code. Peer reviews of process artifacts are also considered a type of inspection. Analysis. This technique is based on analytical evidence obtained without any intervention on the submitted element using mathematical or probabilistic calculation, logical reasoning, including the theory of predicates, modeling and/or simulation under defined conditions to show theoretical compliance, mainly used where testing to realistic conditions cannot be achieved or is not cost effective. Demonstration. This technique is used to show correct operation of the submitted element against operational and observable characteristics without using physical measurements, no or minimal instrumentation or test equipment. It uses generally a set of actions selected to show that the element's response to a stimuli is suitable or to show that operators can perform their assigned tasks when using the element. Observations are made and compared with predetermined or expected responses. Test. This technique is performed onto the submitted element by which functional measurable characteristics, operability, supportability, or performance capability is quantitatively verified when subjected to controlled conditions that are real or simulated. Testing often uses special test equipment or instrumentation to obtain accurate quantitative data to be analyzed. Analogy or similarity. This technique, often considered as a type of analysis technique, is based on evidence of similar elements to the submitted element or on experience feedback. It is absolutely necessary to show by prediction that the context is invariant and that the outcomes are transposable. For example, models, investigations, experience feedback. Analogy or similarity can only be used if the submitted element is similar in design, manufacture, and use. Equivalent or more stringent verification actions were used for the similar element, and the intended operational environment is identical to or less rigorous than the similar element. Simulation. This technique, often considered as a type of analysis technique, is performed on models or mockups, not on the actual physical elements, for verifying features and performance as designed. Sampling. This technique is based on verification of characteristics using samples. The number, tolerance, and other characteristics must be specified and be in agreement with the experience feedback. There is sometimes a misconception that verification occurs after integration and before validation. In most of the cases, it is more appropriate to begin verification activities during development and to continue them into deployment and use. Once system elements have been realized, their integration to form the whole system is performed. Integration assembles developed capabilities via system elements in preparation for verification actions as stated in the integration process. Generally, the system of interest has a number of layers of systems made up of system elements at the next lower level. Thus, every system and system element is verified and any findings possibly corrected before being integrated into the system of the higher level as shown in this figure. In this figure, every time the term verify is used means that the corresponding verification process is invoked. As necessary, systems and system elements are partially integrated in subsets or aggregates in order to limit the number of properties to be verified within a single step. For each level, it is necessary to make sure by a set of verification actions that features stated at preceding level are not adversely affected. Moreover, a compliant result obtained in a given environment can turn non-compliant if the environment changes. So, as long as the system is not completely integrated and or doesn't operate in the real operational environment, no result must be regarded as definitive.